Good morning, everyone. Today we will go through one example, one relatively simple example of the exponential of a matrix that will help us to clarify the properties and more or less how do you solve these problems. Let's go to the blackboard. Welcome to class. So we have the following problem. A problem with initial value, also called a Cauchy problem. Here we have a system. This is a matrix equation. This is the initial value. And we are given that, the vector x sub 0, which is the initial value, it's a vector in R3, which is to be expected because the matrix is a 3 by 3 matrix. Now, given the way that this matrix is defined, we see that the first column has a number different from 0 in the first entry, and the following are equal to 0. Then this means that the first equation can be solved without the exponential of a matrix. We will see this now. Let's copy here the equation, which is equivalent to this expression: minus 2, 0, 0, 1, minus 2, 0, and 0, 1, minus 2. Multiplied by the vector x1, x2, and x3. So when you perform these multiplications, you know how to multiply matrices with vectors. So this is in turn equivalent to the following system. Now, this, together with its initial condition, let's say that x0 is equal to this, which is in turn equal to this vector. Alright, so this equation can be solved. And you have the first solution, which is relatively easy to calculate. This is the solution. Then you plug this solution into the second one. So you replace this here. And this will turn into a first order linear differential equation, which can be solved by the general form. You know how to do it. I can write here. In this case, we have, let's write it here, plus p of t x2 equal to q of t. You know that p of t, it's 2. This is equal to 2. Q of t is this one. So I'll just leave it as q of 2. And so you have this integrating factor, which is p of t with the integral of p of t. So this is minus 2t multiplied by the initial condition of this matrix, which we say that will be this one. So we write it here, plus the same by the integral of this times q of t, and this will be it. So you know how to do it. It is not difficult to do so. You can solve this. And you know how to do this integral, so you can solve this. Then you plug that solution into the third equation, and you apply the same formula, of course, replacing this by the corresponding integrating factor and changing the initial condition to x3 0. And so you can solve this, as I'm showing you, without the need of the exponential of a matrix, but only so because you could solve the first equation, right? There are other examples in which you can do some algebraic tricks, which are not too time consuming, so you can just do it. But there are other cases in which it will be very difficult to solve this without the exponential of a matrix, which is the technique that we will cover today. In order to apply this technique, you need to, the first step is to analyze the eigenvalues of the matrix. So let me copy the matrix here. Let's, 0 0. So the matrix A is equal to this. We will go through some properties of the exponential of a matrix that will help us to do these calculations. Well, it's this. All right. So you want to calculate this exponentiation, which is by definition equal to the series. It's an infinite sum, which is the first terms are the following: plus t squared divided by 2 squared plus t cubed divided by 6 a cubed, and so on. As I told you, it is relatively difficult to, without knowing some properties of A, to do this calculation, because this is an infinite sum. But there are instances in which you can do this just, you can go by definition. And those instances are when the matrix A is nilpotent. If A is nilpotent, then this means that the matrix A, the power of the matrix A of some exponent k will be equal to the zero matrix. Of course, k is less or equal to 10. The dimension in this case is 3. I.e., either this is equal to 0, or a squared is equal to 0, or a cubed is equal to 0. So that would be our first attempt, perhaps. But in this case, it doesn't really work, because in each case, this is different than the zero matrix. So this is not going to work. If some of these values were equal to the zero matrix, then you could go by definition and say, okay, so this is equal to 0, and the following will also be equal to 0. Then you can just perform these simple sums and calculations, and you would have the solution. But this is not the case, so we need to do a different, you need to use a different approach, which will be analyzing the eigenvalues of A. So let's copy the matrix A here. Put it here. By definition, the eigenvalues are the solutions of the characteristic polynomial of A, which is equal to the determinant of this matrix minus these terms you know that this is equal to the determinant of A minus lambda, the identity matrix. So this is equal to, since you have this number here and the following are equal to 0, then you can say that this is equal to minus 2 lambda times the determinant of this square matrix, which is equal to this one. And you can do this by multiplication, so this will be equal to cube. So the solutions, the roots of this, if you do this, then the roots are minus 2 in each case. Multiplicity 3. So there is only one eigenvalue of multiplicity 3. In this particular case, in which the multiplicity is equal to the number n, in this case, which is 3, because A is a 3 by 3 matrix, then there is a property that tells you that the matrix A minus lambda identity is nilpotent. And you can call this matrix N. So this matrix is nilpotent. Then this means that either N is the zero matrix, N squared is the zero matrix, or N cubed is a zero matrix. So let's see which matrix is N. Let me copy the matrix again. I think I have it. It's here. So the matrix N is equal to A minus lambda I. So you know that if you replace the value of lambda, which is minus 2, here you will have 0, 0, 0 here, right? So you replace this. This is equal to I minus lambda I. So when you replace this value, this will cancel. The diagonal will cancel. So this is our nilpotent matrix. It has a very nice form. You know that it's different than 0, so this case is wrong. We go to the following. So you multiply it by the same matrix, and you perform the multiplication. The first row with everything is equal to 0, so you can write 0, 0, 0. The second one with the first is equal to 0, 0, 0. And the last one with the first is equal to 1 here, and all the following is 0. So the second is also different than 0, and then the final should be equal to 0, and you can easily see that this is indeed the case. When you multiply this once again by this matrix, this will be equal to 0. So this is a property of this type of matrices. When you have these diagonal of 1s here and the rest of 0, with each multiplication, the diagonal moves to the next place. So since this is already in the corner, there will be no more place to go. So in the next multiplication, this will be 0, and the matrix will be the 0 matrix. So we are in this case, and now you will use the following property. You can write A as N plus lambda I. So when you do the exponentiation like this, there's a property that tells you that if A and V is equal to V and A, these are matrices, then the exponential of A plus B is equal to A and the exponential of B. So this is the same property that we have in complex exponentials. You know that the exponential of zeta plus w, where these are complex numbers, is equal to the exponential of zeta and the exponential of w. And this holds for every pair of complex numbers, right? In case of matrices, it's not true, in the sense that every matrices doesn't hold this commutativity property. But if the matrices are commutative, then you can apply the formula, the property, I mean. So in this case, the matrices are n, which is nilpotent, and the identity matrix, which by definition commutes with everything. So this is always n always commute with this matrix. This is trivially true. So you can have this and this one. Now you can apply this other formula or property that tells you that the exponential of a matrix which is diagonal, let's say diagonal A, B, C, is equal to the diagonal of each term. I mean, the exponential of matrix A, B, C, where there are zeros in all of the other places, is equal to a matrix, to a diagonal matrix like this. So it's like the exponential gets inside a matrix. This is the complex exponential, and this is the matrix exponential. Alright, so lambda times the identity is a diagonal matrix, so you can have this as, and you can write it perhaps better in the left side. So this is equal to this matrix, and 0, 0, 0, 0, 0, 0 times this one. So now, given that this is a nilpotent matrix, you can calculate this by definition. Because when you do this, when you go in this definition, in the case of this nilpotent matrix, this will be equal to 0. Then you only need to calculate these first terms, which it's what we will do here. So A is equal to this diagonal, but you know that this is equivalent, this multiplication is equivalent to just multiply this scalar by the result of this matrix, because this is a diagonal matrix with constant coefficients. So this is equal to times the first term of the series, which is always the identity matrix, plus Tn plus t squared divided by 2n squared plus, and the following will be equal to 0, right? And the following also will be equal to 0, so we stop here. And this will be equal to, you know that the identity is 1, 1, 1. You know that the nilpotent matrix is this one. This is the nilpotent matrix. So you can write t and t here, and the n squared is equal to a 1 in this position. So you multiply this one by this term, so you will have divided by 2 and 0, 0, 0 here. So the result is, no need to write it again, I think. This is the result. So our method tells us that if you have this exponential with initial value here, then its unique solution is, now we have calculated this term, this is also given, then the solution is equal to which is then equal to this following vector, which we can write here. You multiply this by this, so this will be, and you can now replace this by its value, which is -2, right? Oh, wait. I think there's a mistake here. Oh yeah, I forgot to write this term t. When you multiply it, it's lambda t identity matrix. So this is lambda t, and this is also lambda t. This is lambda t, so this is -2t. -2t. The second term will be this row multiplied by this, so it will be x10 t a -2t plus x20 e -2t. And the last term will be this by this. We can factor this perhaps like this. And in the middle we'll have x30 plus t x20 plus t squared divided by 2 x10. So this is the solution, and you can check that this is true with the traditional method, which is the first term is the same, right? It's exactly the same. And the following will also be the same. So in this case, given a quick review, in this case we have used these properties first. Well, you know the property that the determinant of a matrix can be calculated by taking one of the rows or one of the columns, assigning signs. This is plus, minus, plus, and you can have this determinant equal to this entry times the determinant of the following plus this entry times the determinant of this matrix that has these columns plus this number multiplied by the determinant of this square matrix. So in this case, since these are equal to 0, then you only have to multiply this term, this entry, by the other side of the matrix. So we use that property, and we use this property here, that is, if there's only one eigenvalue, then this matrix is nilpotent. So this was the perhaps important property that we used. After that, we only had to do some minor calculations, which were relatively easy. If you knew this property, you didn't even have to do any calculations. You already knew that n squared will be this one, this is n squared, and n cubed will be 0. So this was quite trivial. Then the other important property was this, that if two matrices commute, then you can have this property. And this is important because this pair of matrices always commute, because the matrix of the right is the identity plus a scalar, which commutes everything. So we apply that here. And lastly, we use the property that a nilpotent matrix has an exponential, which can be calculated just by the first n terms, or less than equal to n. In this case, we only had to calculate the first 3 because n cubed was already equal to 0. And we did that. We had this matrix here. And lastly, we used the main theorem of linear differential equations, which was that the solution of this initial value problem is unique, and it has this form. So the solution, we replace it here and we multiply by the initial condition, and we have the solution here. So this is the last property. So in summary, we use 1, 2, 3, this other property, 3 properties. Perhaps this is not a property, 4 properties. We use 4 properties, 5 properties, 7 properties. So it's a kind of a lot of theory perhaps, but it really pays off when you can solve this by this, say, basic method. So that's why we have to know why we have to study the exponential of matrices. So this will be it for today. If you have any questions, you can write it down in the comments. I will do my best to try to answer them. And also, if you have any suggestions about another topic that you would like me to cover, I can try my best to cover that in the next video. So see you around, guys.